Prime numbers are so fascinating. They've been studied for at least a couple thousands of years, and we have yet to find a way to predict their placement in sequence among all natural numbers. I just want to share some interesting things I found out about them. Maybe someone can explain what's going on here. It may all come down to some trivial concepts, but who knows? Let's start by applying the sine function to the prime numbers. Seems like a mess, right? Well, not really. I can see two distinct patterns there. More specifically, two phase-shifted sine curves. The red one, I will call f plus, because of the plus sign inside the parenthesis, and the black one, I will call f minus, because of the minus sign inside the parenthesis. It just happens that the sign of all the prime numbers sits on those two phase-shifted sine curves, except for the prime numbers 2 and 3. We'll summarize all open questions at the end of the video. Now let's go on. I initially determined the two constants empirically, in order to catch the best fit to include all prime numbers up to around 100,000. With a decent number of decimal digits, I've been able to identify the constants. Constant 1 turns out to be pi over 3 minus 1. Constant 2, the phase shift, turns out to be 2 pi over 3. Therefore, here's the compact notation for both functions f plus and f minus. Wouldn't it be cool if the functions f plus and f minus determined the prime numbers only? Well, sorry to tell you, but all the multiples of all the prime numbers, except for any multiple of 2 and 3, sit on those curves too. Let's first see what happens to the multiples of 2 and 3. Let's take 3 times 7, which equals 21. The sign of 21 definitely doesn't sit on our curves f plus and f minus. The same applies for 2 times 19, which equals 38. Just another one. Let's take 3 times 89, which equals 267. Definitely off pattern. Let's now see what happens when we multiply two prime numbers other than 2 and 3, depending on which curve they sit on. For example, let's take 7, which sits on the plus curve, times 13, which also sits on the plus curve. The result is 91, which sits on the plus curve too. Trust me, this happens for any two numbers on the plus curve. Doesn't it resemble positive times positive equals positive? Let's now take 5, which sits on the minus curve, times 23, which also sits on the minus curve. The result is 115, which instead sits on the plus curve. Again, trust me, this happens for any two numbers on the minus curve. Doesn't it resemble negative times negative equals positive? There's one case left. Let's take 7, which sits on the plus curve, times 29, which instead sits on the minus curve. The result is 203, which sits on the minus curve. Once again, this happens for any two numbers that do not sit on the same curve. Doesn't it resemble positive times negative equals negative? Now, a summary of all the open questions. First, why don't prime numbers 2 and 3 follow the rules? Do they really belong to the set of prime numbers? Or, are they actually some, let's say, otherwise nice numbers, which happen to be prime just because they're so small? Could we call them subprimes? Second question. Why do prime numbers follow those patterns and why two different patterns? Are there two distinct types of prime numbers, depending on the pattern they follow? What are possible observable effects of this dichotomy? Third question. Besides the analytic explanation, is there any deeper meaning behind functions f plus and f minus behaving like positive times positive equals positive, negative times negative equals positive, and positive times negative equals negative?